Is the universe hiding extra dimensions we can't see? Could a graviton, a particle we don't even know exists, change everything about the cosmos?
The only particles that can move through the extra dimensions of space are the gravitons.
And what does the future of physics hold if the standard model should happen to fail?
It would actually surprise me if the standard model of cosmology holds up to scrutiny over the next decades as we learn more and more about this piece of time.
I had the pleasure of exploring all these advanced concepts and more with the renowned cosmologist and physicist Dan Hooper in his former office at the University of Chicago. Now he's moved to the University of Wisconsin-Madison. Go Badgers, where I spent some time at the end of my graduate student career. In this thought-provoking conversation, Dan and I challenge and explore how hidden dimensions and mysterious particles can fundamentally challenge our understanding of the universe. So let's dive deep into the fabric of the cosmos.
Welcome to a very special episode of the Into the Impossible podcast with a colleague and friend and past guest on the podcast, Dr. Dan Hooper of the University of Chicago and Fermilab for now. Can we say what else is happening?
It'll be announced next week.
So something else is happening. By the time this comes out, it'll be out there. We're actually in person, even though it looks like we're recording on Riverside. Say hi to Dan. There he is. So this is dueling laptops across the beautiful .eduroam network. So we have a new tradition since you've been on for your last book, At the Edge of Time. What was it?
At the Edge of Time, yeah.
Phenomenal book. Everybody should pick that up. One of your 5. How many books have you written now?
3 plus the textbook.
And then the textbook is right here, and I was going to buy a copy, but you saved me $75. This is an incredible addition to the oeuvre of graduate student level cosmology, and actually covers and updates a classic that we've talked about before, which is Kolb and Turner. And I'm interviewing your colleague Rocky Kolb tomorrow on the podcast, along with Wendy Friedman while I'm here. You guys are blessed. So what we do on the podcast is we love to do what you're not supposed to do, which is to judge a book by its cover. So Dan, take us through this wonderful book's title, and there's no subtitle, but what is this cover? Are these epicycles? What's going on here?
You know, I don't know if it's like literally anything, but so Fermilab for many decades had an artist in residence, Angela Gonzalez. She did many of the posters and much of the artwork around the lab. But she retired and then passed away years ago. But this is actually a piece that she did before working at Fermilab. And to me, it just struck me as evocative of cosmology, even if I can't point to the objects in the painting and say, like, these are such and such, you know. Yeah, it's more, more abstract.
I've been looking through a couple of your recent research. I should also mention you're the host of the Why This Universe book.
Mm-hmm. Along with Shalma Wegsman. Yep.
Shalma Wegsman. She's in Columbia?
Well, she's in New York, but she's working in tech these days.
Oh, she is. Okay, great. I'll put a link to the podcast down below. You should all subscribe. It's one of my favorites. But today I want to talk about a research paper that we've read about as a way to kind of do the impossible, which is to kind of break down some of the most advanced concepts, which actually have some of their origins 100 plus years ago. And that's Kaluza Klein theory and this new paper that you have about extra dimensions and gravitons in the early universe and how they could potentially decay. And I want to ask you, first of all, Kaluza Klein, can you explain that in relatively straightforward terms? What is it? What were Kaluza and Klein trying to do? And what has their legacy been?
So it goes back into the 1920s. These mathematical physicists, Theodore Kaluza and Oscar Klein, independently made contributions to this idea that you could maybe fit the equations of electricity and magnetism, what we call Maxwell's equations, into the general relativity framework that Einstein had for gravity. But to do this, you needed a 5th dimension. So the 3 plus 1 normal dimensions of space and time, along with a 5th dimension. Now, if you casually look at our universe, it doesn't seem to have an extra dimension of space. So they tried to make this all hold together consistently by saying, well, that 5th dimension is curled up in a little circle. So imagine that we're taking our macroscopic universe, and imagine that if you went far enough in that direction, you'd eventually come out the opposite side, okay? So that's what we call compactifying a dimension. So imagine now that there's a 5th dimension and it's compactified, but it's compactified in a very, very short distance. So you kind of go around in a very rapid circle, and that circle is so small that you don't notice it. This is the sort of thing that Kaluza and Klein posited to try to make these theories play well together. Turns out not to work for a bunch of technical reasons, and I don't think it's super enlightening to go into it. But jump several decades later, and people in the 1980s start to be excited about theories of extraspatial dimensions again, including ones that are compactified. And some of the features of these old Kaluza-Klein theories come back into vogue. One thing that is exciting about these theories, or one interesting thing about these theories, is if I, as an observer in my normal 3+1 dimensional space, am looking at a particle, and that particle is moving in the extra dimension, I don't see it moving. It looks stationary to me, but it has a bunch of kinetic energy. And according to Einstein, something with a lot of energy that isn't moving is something that has a lot of mass. After all, E equals mc squared just means energy is mass, mass is energy. So these particles moving in these extra dimensions look like normal particles with just a lot of mass. So I could take an ordinary electron, have it move around that extra dimension, and to us, it will just look like an electron with way more mass than a usual electron. And it turns out that there are different kind of standing mode configurations of these particles. You can have them move with one wavelength around the extra dimension, or 2, or 3, or 4, all the way up to infinity. And each one of these will be a particle with a different amount of mass. We call these things Kaluza-Klein modes, or Kaluza-Klein states. And there's a whole tower of them in these theories with extra dimensions.
And to think about the impact on gravity. So when we talk about these particles or so-called Kaluza-Klein gravitons, first of all, what is a graviton? Mm-hmm. And second of all, how can it decay? I thought they were massless and travel at the speed of light.
First of all, we don't know that gravitons exist, okay? Just full disclosure right off the bat. But the other forces, not gravity, but the other forces we know about in nature, so the electromagnetic force, the strong nuclear force, and the weak nuclear force, are all communicated through space by particles, things we call bosons. So the reason charged particles push and pull on each other is because they're passing photons back and forth through space. The reason the strong nuclear force exists is because they're passing gluons back and forth through space. And the weak nuclear force is communicated by things we call the W boson and the Z boson. We speculate that gravity too is communicated by some sort of boson, and we call those bosons gravitons. They're different in some technical ways compared to other kinds of bosons. Instead of being spin 1, they're spin 2. If you know what that is, great. If you don't, it's just a technical detail. But probably, according to many people who are thinking about quantum gravity, gravity is somehow made up of these particles called gravitons. And like you said, they're massless. But now imagine that you've got a graviton moving in an extra dimension. To us, that graviton looks like it has mass. And if you imagine now that graviton moving less quickly in the extra dimension, it would look like its mass goes down. So you could imagine that graviton losing energy, giving it off to something else, and decaying into a lower energy state. It would look to us like that graviton is decaying. Also, that graviton could lose a bunch of its energy, kinetic energy, giving off, producing new standard model particles like photons or electrons or whatever, and that would look to us like a Kaluza-Klein graviton decay.
If you have the same kind of extra compactified dimensions, how do you prevent that same mechanism from giving the photon, which we know almost for certain has zero mass? How do you prevent that from acquiring mass simultaneously? Doesn't it come up naturally that you would expect both massless so-called particles to have, bosons to have effective mass behavior?
There are different kinds of extra-dimensional theories out there. In some of them, all of the particles can move through all dimensions, okay? And then you're right. Just like the gravitons can have Kaluza-Klein states, the photon can have Kaluza-Klein states, and so on and so forth. And the photons we see and observe are the what we call the zero mode. They're the ones that aren't moving in the extra dimension, and they don't seem to have any mass. But in principle, you could create Kaluza-Klein photons that do have mass, but they have to be heavy enough that we can't produce them at accelerators. Otherwise, we'd know about that already. In other Kaluza-Klein theories or other kinds of extra-dimensional theories, the only particles that can move through the extra dimensions of space are the gravitons. Okay, and everything else is confined to a three-dimensional spatial structure we call a brane, B-R-A-N-E. And that's the kind of one that my paper considers. So in that one, there are no Kaluza-Klein states of the standard model fields. The only thing that gets a Kaluza-Klein tower are the gravitons, because it's only gravity that can move through the extra dimensions of space.
Do we have any limits from, say, the gravitational wave 1708, 17? Colleague David Spergel, Dan Holtz, Maya Fishback, and Chris Pardo had a result. I'm just looking it up. I didn't memorize it.
Sure.
But I do recall that, a limitation on space-time dimensions. But wouldn't the concomitant observation of electromagnetic multi-messenger signal along with gravitational waves, wouldn't that put some limits on the maximum allowable mass of gravitons?
Indeed. So we have constraints from a bunch of different things on models with extra dimensions. The gravitational wave production is certainly one of those things. We have some from the early universe. We know that whatever went on in the early universe, it couldn't have screwed up our observations too much because they look like what we'd expect they would look like. And then machines like the Large Hadron Collider tell us a lot about these models. In fact, we know from the Large Hadron Collider that the dimensions can't be very big, and they can, and from that we can kind of set boundaries on this sort of thing. We also know from, for example, there are not a lot of Kaluza Klein gravitons being produced in the cores of hot stars. And that tells us things about how many extra dimensions of what size can exist. So we have constraints from a lot of different kinds of observables on this class of models.
So, we're here meeting for the Simons Observatory face-to-face, hosted by your colleague, Jeff McMahon. And one of the greatest holy grails in all of cosmology now is to uncover gravitational waves as a byproduct of inflationary perturbations, which have never been seen before.
It'd be incredibly exciting if it were to come true, yeah.
Yeah, we know that was the case from the BICEP affair of 2014, and it's been 10 years since then. But there's people in this building, your friend and mine, John Karlstrom, leading the efforts along with many, many other scientists. CMB stage 4. Sounds like a disease, but it's not. But this question of what would be the impact on early universe observables? Would this make our jobs harder as experimentalists because it would be effectively adding a range and Yukawa decay and so forth? Would this lead to a suppression of our ability to detect these primordial gravitational waves?
If there are extra dimensions of space, then the early universe could have played out very differently than in the standard picture. So when I started working on this project, I had a different goal in mind than the paper ended up being. I was interested in these kinds of models with extra dimensions in the possibility that particles could collide and make very small black holes that would very quickly evaporate away. And those black holes could produce a bunch of interesting stuff like dark matter or dark radiation, things like this. But when I found examples of models that could do this, I found that those same models tended to screw up the production of the light nuclear elements in the process we call Big Bang nucleosynthesis. So in standard cosmology, starting about a second after the Big Bang and going a few minutes after that, all of the deuterium and helium and a little bit of the lithium, all the stuff that we find in the universe was basically forged then. And we measure this stuff and it agrees with the predictions. So the standard theory has to be, pretty close to right. And in a lot of these models that I was interested in, you wouldn't get the right predictions at all. You'd get way too much deuterium and way too little helium and these sorts of things from the Kaluza Klein gravitons decaying during the era of Big Bang nucleosynthesis. So I was forced to kind of abandon the idea that you could make these black holes really abundantly in the early universe, and I had to kind of go in this direction. But that means, frankly, everything we think we know about the first tiny fraction of a second after the Big Bang could be very, very different. And until you have a complete theory of quantum gravity that tells you how all this fits together, how we would embed something like inflation into a theory like this, I would be very hesitant to say what the Simons Observatory should expect to see or not see. In fact, I think we should keep a maximally open mind when it comes to the first fraction of a second after the Big Bang. It would actually surprise me if the standard model of cosmology holds up to scrutiny over the next decades as we learn more and more about this piece of time.
That would be very surprising, of course, and counter to the factual way that cosmology has evolved over time, where surprise after surprise. I got so many questions. If God told you that spin 2 particles do exist, that gravitons exist, what would be a betting man's odds on the existence of spin 3/2 particles, which we almost hear nothing about? But if you knew, would it influence it at all, first of all? And second of all, would we have some other reason to expect that they might exist?
Yeah, so a really popular and well-motivated mathematical idea that gets thrown around in theoretical physics circles all the time is that of supersymmetry. And in supersymmetry, there's a fundamental, relationship with the things we call fermions and bosons in nature. Bosons are particles with integer spin, like spin 0 or spin 1 or spin 2. Fermions are things with half integer spin, like spin 1/2 or spin 3/2. And the graviton, if that exists, that spin 2 particle exists, and if supersymmetry is manifest in nature, and there are compelling reasons to think it very well might be, then there really should be spin 3/2 particles. We call these things gravitinos, and they are the supersymmetric partner of the graviton. So if those two things are true, and it takes both of them, gravitons exist, and supersymmetry is manifest in nature, then you should really expect there to be spin 3/2 particles as well.
What's a force? Last time you and I spoke, we were talking about G-2, the result that we haven't heard quite as much of the hoopla that was sort of surrounding it. A new force discovered. What's the current status of G-2? And also, what would be the correct interpretation of a force? Would it be, we hear a lot, gravity's not a force. We hear, a weak nuclear force is a force. What does it mean to be a force? And then what's the latest on G-2?
Yeah, so a lot of this is semantic. If you want to call gravity a force, by all means.
Me too, yeah, I feel the exact same way.
The reason that people say gravity's not a force is that in Einstein's theory, basically he said, well, the reason that there is this phenomena we call gravity is because space and time geometry gets warped or curved or whatever because of the presence of mass and energy. And things move through space in the way they do, not because something's pushing or pulling on it, but because of the shape of that space and time. And if you understand the geometry of space and time, then there's really no force of gravity at all. There's just a consequence of that geometry. And that's fine. That's all true. I mean, that's a very good way to think about it. But effectively, gravity feels like a force. Like I feel like I'm pulled down towards the earth. And if you want to think about gravity as a force, that's a perfectly fine thing to do. The other forces in nature, though, are we understand a little bit differently. We don't think that electromagnetism or strong or weak nuclear forces are the consequence of the geometry of anything. We think instead particles are being passed back and forth through space, communicating these forces. I said before that the photons bring the electromagnetic force into existence. Gluons bring the strong nuclear force into existence. The W and Z bosons bring the weak nuclear force into existence. It is completely possible, likely even, that there are other forces that are brought into existence with other particles. Maybe these forces are so weak that we don't notice them readily. Maybe they only work at really high temperatures or something like this, and things like this. This connects to G-2 because these measurements over the years of this thing we call the magnetic moment of the muon, basically how a muon spins in the presence of a magnetic field, haven't agreed exactly with the predictions of the Standard Model. There are different ways to explain this. One that I've worked on is that there could be a new force-carrying particle, a new weak force, distinct from the other known forces. And this would kind of all hold together kind of nicely. Some of the wind has been taken out of the sails of this idea recently because as physicists providing a technique or carrying out a technique called lattice QCD or lattice quantum cryptodynamics, have tried to calculate what the Standard Model prediction for this number is, the magnetic moment of the muon. Some of those calculations have found numbers that agree with the measurements more than the old numbers. So it's possible there's not a mystery here at all, and that the measured value agrees with the predictions of the Standard Model, which, I guess is a good news for the Standard Model and is holding up to scrutiny even more, even longer. But if I'm honest, it would be very disappointing because I want to discover new physics. That's what I'd like to see happen. There's still one other mystery, which is there's another way to estimate or to determine what we think the Standard Model prediction for the muon's magnetic moment is. We call these the R ratio measurements, and they're based on other measurements of other quantities. And those still predict a completely different number or a very different number. And no one really knows, why does this one technique tell you it should be one thing and this other technique says it's another? I don't have a good answer to that yet. I think it's a pretty confused situation, at least for the moment.
Another thing that has been, kind of permeating the zeitgeist is the hint from the Desi experiment, which was in part co-led by one of the leaders of one of the byproducts of the Bicep 2 debacle or affair, in some senses, that we didn't really have any external auditing of our results. We kind of checked results internally. We didn't really vet it with other experimentalists. We showed it to some theorists and so forth. And obviously people like Andre Linde and Alan Guth were very self-interested in it for good reason. I would be too. But we didn't really have an external board that was auditing us. And so what the Simons Foundation has really implored us to do and made us do, for good reason, is to have an external group of advisors. And some of them are located here, including Josh Freeman. And I think this is really good for science and for transparency and accountability, which is somewhat lacking. I always think it's kind of a shame that our colleagues in the law school and the med school and the business school teach their students ethics. And we almost never get taught ethics to our students, right? But anyway, the results that Josh and some of his colleagues worked on with the Desi experiment, pivoting 100%, seem to suggest two interesting things. Some interesting behavior of neutrinos, which I want to get your impression on as we conclude before I go back downstairs to my meeting. And then a hint that dark energy might not be a cosmological constant. Can you talk about those in either order?
Yeah. I think we should view the Desi results as like maybe an inkling or a hint or something, but probably not anything stronger than that. The claims they're making are not super statistically significant. And also, I wouldn't be surprised if, as time went on, some of their measurements get refined, and maybe the techniques change slightly, and we find slightly different answers than we're currently looking at. That being said, these are interesting hints or inklings. As far as neutrinos, that one thing cosmological surveys can do is try to measure the total mass of the three neutrino species. So it's actually sensitive to the sum of all three neutrino masses. Based on the way that neutrinos turn into other kinds of neutrinos, what we call neutrino oscillations, we should expect the sum of these three masses to be at least 0.06 electron volts, I think is the number. And based on other cosmological measurements, they could be up to about twice that. Okay, so there's a kind of a narrow window where they could live. And the Desi results really seem to want to push that even farther down, like farther than the standard model or what standard understanding of neutrinos would allow. In fact, if they were massless or even negative in mass, that would fit the data a little better. And nobody thinks that neutrinos have a negative mass. I don't think anyone thinks they're massless.
Hey there. Are you enjoying this in-depth conversation with the renowned cosmologist and astroparticle physicist Dan Hooper? Well, there's plenty more where that came from. And if you're excited about uncovering the mysteries of physics from black holes to the Big Bang, I know you're going to want to subscribe to this channel, not just watch the videos or listen to the audio podcasts. Please make sure you follow and subscribe where appropriate, because that's what the algorithms want. These are mysterious forces, more unknown, more inscrutable than dark energy and dark matter itself. But we have to play by the rules if we want to keep getting great guests like Dan and so many more to come. Don't forget to leave a comment or a review. That really helps. An asterism, a small mini constellation of 5 stars or so, will be most appreciated. And now, back to the episode.
Dan Green has a lot of papers about that recently, or explanation. But as I understand it, it's sort of a nomenclature, almost like a nomenclature. They would behave as if a negative particle would in terms of their clumpiness, but that doesn't necessarily mean they actually have negative mass.
Yeah, no, I don't think there's any sensible way to think about negative mass neutrinos. But also, it doesn't seem that they should be quite as light as the Desi data seems to prefer. So again, it's not that statistically significant. It might be that this all holds together just fine in the future, but right now it's kind of pushing us in a weird direction. And then in terms of dark energy, the standard, what we call lambda CDM paradigm, which is dark energy in the form of a cosmological constant plus cold dark matter, that seems to not agree very well with this data as well. A cosmological constant is just a form of energy that doesn't change in its density with time or place. It's the same density everywhere at all times and all places. And that means as the universe expands and space gets bigger, the fraction of the energy that's in the form of dark energy goes up. So as the universe expands, eventually dark energy becomes the main thing in our universe. And that's something that's been true for the last few billion years of our universe's history, and it will be only more true in the future as long as that density stays constant. But the Desi results seem to suggest that maybe the amount of dark energy has been changing over the last few billion years. If that were true, it would be an enormously big deal. Dark energy wouldn't be a cosmological constant. It would be something else, something that evolves over cosmic history. There are lots of these theories. They usually go by the name of quintessence. It's hard to write down a theory of quintessence that agrees with all the data. There are a lot of constraints on it, but some do, some are okay. And again, not super statistically significant. We're just seeing the very, very beginnings of hints. But if more data were to confirm this, it would be a really, really big deal for cosmologists.
And I'd like to wrap up with a question I always like to ask my colleagues, distinguished colleagues, and it relates to the progenitor of the name of this podcast, Arthur C. Clarke, who said many things, including the only way of discovering the limits of the possible is to go beyond them into the impossible. That's the name of this podcast's origin. But he also said the following, and I'm not calling you old, but he said, when an elderly but distinguished scientist says something is possible, he or she is very likely to be right. But when he or she says something is impossible, they're very most likely wrong. I want to ask you, Dan, what have you been wrong about? What have you changed your mind about in the last few years, if anything?
I don't know that I've gone from completely confident in something to completely rejecting it in that time, but a lot of things I've shifted my thinking on. We talked about the muon's magnetic moment, right? If you asked me a few years ago, I would have said, like, there's a pretty good chance this is an indication of new physics, maybe a third, maybe a half or something like this. It seems much lower now. As these lattice QCD calculations come in, I have no choice but to reevaluate the situation and take that data into account. And it's probably not the case that this is new physics. A few years ago, I was hearing rumors that the IceCube collaboration, this neutrino telescope at the South Pole, was detecting neutrinos from this nearby galaxy, NGC 1068. And I looked at this object, I looked at its emission at different wavelengths, at different kinds of light. And it was not being seen at very high energies, like at TeV scale photon energies. And I crunched some numbers. I was working with a student of mine at the time. And we just this thing can't make that many neutrinos. It just can't. It just doesn't work. A year or something passes, and that rumor gets elevated to a real paper, and they do a press release and everything. And they think at very high statistical significance, this thing makes neutrinos. And went back to the drawing board, and me and the same student and a couple other collaborators stared at this and what were we assuming that turned out to be wrong, that can explain why these neutrinos can come from the source, even though we were so sure they couldn't. And we wrote another paper explaining how the source, in fact, could make those neutrinos. It's not super easy to do. It's a weird environment requiring really big magnetic fields and super high energy densities in this dense corona around the galaxy's supermassive black hole. But I think that's the right answer now, and or something very close to it anyway. Something that I thought was impossible a few years ago.
Those are the kind of good surprises when you find out that you're wrong. It's like Einstein's biggest blunder was saying that he made a big blunder when he included the cosmological constant.
I certainly don't mind being wrong occasionally.
Dan Hoover, thank you so much. Good luck with everything in the future, especially your new books and papers, and look forward to maybe catching you in concert sometime.
If you're into physics-themed punk rock, check out the Spectral Distortions. You can find us on Spotify or wherever you listen to music.
And your podcast as well.
Why This Universe?
Thank you, Dan. It's been a pleasure.
Thanks.